Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, back to back from the last one, if you just came from that one. All math-based, of course, and as always, it is an honor and a privilege to be serving you. Do you guys know the script by now? Do you know what I say here? Are you repeating me like, what's that? Shane Company. Are you guys repeating me like I say it there, or are you just like, you fast-forwarding past the intro? I have to find a proper intro someday. Anyway, guys. The last video that I covered was a set of practice problems. I think only 8 practice problems, but pretty extensive as far as what I was able to get out of it regarding corresponding parts in similar figures. And now we're just going to look at similarity in triangles only. Now, if you want to look at a lecture video on similarity in triangles, there was one that was uploaded just a few days ago. I don't know, 4 days ago or 5, I don't know, something like that, pretty recently. And you probably want to watch that one before this one. I'll talk about things here that's probably going to assume you've seen that or that you've been exposed to some of that stuff before. And I think my last video was kind of like that too, but I think I hit or watch the last video. But this angle stuff, it's going to be a little new. That was not in the last video that I just did. So I'm going to do, I think, 15 practice problems on this one here. And one of the things that's going to get a little heavier, which I kind of mentioned I didn't like in the last set, was there's a focus a little bit on a lot of decimals in this one, and I'm going to play with decimals a lot. You're going to learn I'm not a fan of leaving things as decimals when I can work out a fraction answer, not using a calculator. I like to be precise. I like to work things in that way. So if you get lost on those parts, honestly, I'm going to say it's not the biggest issue. Focus more on the geometry parts, the proportions specifically, and the corresponding angles and the orientations and the conjectures and stuff, the similarity statements. I think those are going to be the bigger parts you get out of it. Skip past the decimal numbers or use your own numbers if you'd like to in those instances and kind of just hear what I have to say beyond that. But if you want to improve your thing with decimals and fractions and the like, then kind of be alert at the same time. All right, guys, I'm already 2 minutes through this video. I want to go ahead and get started with you. And this is out of a textbook for me. I'm going to do numbers 3 through 17, straight up, no skippies. And sometimes I'm going to go beyond kind of what the instructions ask, but these ones are pretty good so far. Determine whether the two triangles are similar. If they're similar, write the similarity statement. I'm also going to justify that reasoning by either using angle, side, or side. Now, I know from the basis of the book alone that they want to focus on the angle concepts most, and you'll also notice that because they don't label any sides that would not only correspond, but we could also set up a proportion with. So we're hunting for angle on the first few sets of problems, guys. If I can find 2 different pairs of corresponding angles congruent with one another in the 2 triangles, then I'll have 2 similar triangles there. Okay? So, and then we'll write a similarity statement from that. So let's go ahead and get started here. Now, these do not mean that these two are congruent to each other. I don't even know why those 2 things are there, but they do give us angle measures here. And they have the angle A, the measure of angle A is 65 degrees. The measure of angle D here is 65 degrees. I think it's safe to say that these 2 angles and these 2 triangles are congruent. We can assume that they correspond or try and make use of them corresponding right now. Angle A is congruent to angle D. We have 1 set of angles so far congruent. So as far as angle goes, there's an angle. Angle pair. Now, angle B is not congruent to angle F right there. We have 48 and 67. They are different numbers. Does that mean that these 2 triangles are not similar? Maybe. But we don't have any information right now about angle C here or angle E here, and we can discover it because we do know that triangle interior angle sums are a constant 180 degrees every time. So I could search and dig for one of these. Let's go and find this one here. Let's find the measure of angle E by saying if I add 65 with 67 with the measure of angle E, that should be, guys, that should be 180 degrees. Now, my hope is that the measure of angle E is 48 because, or as far as if I want to make them similar, because that's the only other angle that can be to make this thing work. So 65 plus 67 is 132, and if I subtract 132 from 180 here, I am going to get 48 degrees right there. So measure of angle E is 48 degrees, and you know what that means is I did find a set of, once again, corresponding angles that are congruent right here that says angle B, and one triangle is congruent to angle E, and the other triangle, excuse me, I have another pair of congruent angles. Now, I could have tested angle C. I could still do it if I wanted to, or I could have done it early on. The point is this will be 67 without testing because that's the same 65 and 48 as this is. And of course that leads to 67 because all triangles add to a constant 180. I don't need that part though, guys. And that's actually the reason I don't need that, because you know it's going to be. That's why we only need two angles to be congruent, two sets of angles to be congruent here. So what we're going to say now is the similarity statement, which means state that one triangle is similar to the other. And I'm going to say this is going to be by angle. So there's more than one way to write this out. It all depends on how you write out the first triangle that you choose. And you can choose any letter order that you'd like if you're permitted to, which for me you are. I'm just going to go alphabetically, triangle ABC. You're going to see me do that a lot. In some cases, like I think this one's true here, since A is congruent with D, A corresponds. A is the first letter, D will be the first letter. B corresponds as congruent with E. B is the second letter, E is the second letter. And it looks like F's that third letter with C, which are both 67. So A, B, C, D, E, F. Again, that kind of happens a lot. Here's the similarity statement. They are similar by angle. All right, one question down. All right, next question here, number 4. Here I have two triangles next to each other. They share the segment AC. These are both marked right here to show two congruent sides in this triangle. That makes this triangle isosceles. And in an isosceles triangle, we also have congruent base angles. B and C are congruent to each other. This is not an example of an angle set for angle, because these are two congruent angles in the same triangle. We want congruent angles in different triangles, parts that would correspond and be congruent. So they're isosceles, though. That's maybe helpful depending on how you want to attack this problem. I already think of a way that I can. We'll see what I do. Now, these are also congruent, these are congruent, so this triangle is isosceles right here as well, which means I have another pair of congruent angles inside this triangle. These two angles do not have to be congruent to these two, though. As you can tell, this kind of fattened out here. Looks like these angles are maybe a little less there. But here's the thing, if this is 78, this is also 78, which is probably helpful for me because what we do want to find here, guys, once again, we're hunting for angle here. We want to see if we do have two similar triangles in ABC and, I don't know, I guess ACD, however it is that these would correspond. But you know what does probably correspond is, because these are isosceles triangles, is the vertex angles probably correspond. So my first test, and probably the only test I might need to check and see, is do these two angles match up in a way that they're congruent with each other? Does this A, or CAD, is that congruent with BAC right here? And the way to figure it out is figure out this angle measure by knowing I got 78s. These add to 180. Let's check it out. 78 plus the measure of angle CAD is 180. CAD is this one right here. That's 156. And if I subtract 156, I don't think that's 16. I think that is 24. So that's 24 degrees right there. Because this 24 corresponds with 16, and you might be going, wait, how do you know? Once again, if these are isosceles triangles, the vertex angles are probably going to have to correspond. And I don't say probably isn't, probably, they will. Those are the ones that are going to have to correspond with each other, because that's the only way that these two sets can be congruent to each other and then congruent to these guys. But these are different. And as long as these are different, that's not enough information. These are definitely not similar. We don't have congruent corresponding angles. I could have done the same thing here, trying to solve for these two same missing angles here. If I do it right in my head, those would both be 82. So these would both be 82 here, not the same as 78. No congruent angles, no angle. These are not similar. And if they're not similar, you don't have to write a similarity statement. You don't have to say ABC is not similar to this by not angle. You've shown enough to determine that no corresponding angle sets, therefore not similar. All right, let's move forward here. Let's look at 5 and 6. Same instructions. And same thing I'll be doing regardless. All right, number 5. In these two triangles, I see that angle A is congruent to angle E. And, right off the bat, I see vertical angles right here. A very popular thing among these kinds of shapes here. I could say angle C congruent to angle C, but I think I have to be a little more specific and talk about in this what that angle C is. That's angle ACB. Angle ACB is congruent to angle, we can call this ECD. And I am a little careful as far as I didn't say DCE. There's nothing wrong with saying DCE. It's the same angle. But I try and match parts that I already know correspond. I know A corresponds with E, so I'm putting A first I'm putting E first like I put A first. It's something that might help when I make a triangle similarity statement. You never know. Anyway, guys, I already do have angle, angle here. This is already set up. Angle, angle. These two triangles are similar. They are. One's a larger version of the other. It's just kind of rotated and stuff. So what can I say there? I could say triangle ACB. How about this? Triangle ACB is similar to what triangle? Well, we already found out that A corresponds with E, right? And C corresponds with C, the two C's right there. So this is indeed ECD, just like I put here. Pretty cool, right? By angle, angle. Now, you might be curious, Mr. Robinson, is there a way that I could have possibly found out, because you could have in the other ones, is there a way I could have possibly found out that D was congruent to B without ever having known the vertical angles here? The answer is yes. And here's how. It has to do with A being congruent to E. A is congruent to E, and those are known as alternate interior angles. Right there. Look at the green. You guys see the green right there? See those alternate interior angles? When alternate interior angles are congruent, you know what's true? The lines that make those parts are parallel. When you have alternate interior angles, you do have... Whoopsie, I hit the wrong button. Let me pause. I went to the end of the book. Okay, sorry. I hit the end button. I was trying to hit the delete button. Let's try that again. Delete. All right. When you have alternate interior angles, you do make parallel lines. And you know what happens when you have parallel lines? You also have alternate interior angles right here. Yes, those are alternate interior angles and they are congruent. So you use alternate interior angles in one transversal to find parallel lines, and then you use those parallel lines to then find alternate interior angles. Very possible to do and come up with those two congruent to each other without using the vertical angles ever at one point. I'm not going to do that, but yes, angle B is congruent to angle D. But we already found our angle, angle. Nice to be creative every so often, right? All right, and you know what? It's helpful for number 6. You look at number 6 right here. We know that angle D is congruent to angle, I can't just call that C. That I call it ACB. How about that? Angle ACB. Right there, that's a given. And, you know, sometimes we got to go hunting a little bit, but I see parallel lines. They tell us that. It's really important to try and seek a transversal that forms angles within both separate triangles. I got a triangle here and a triangle here. And this transversal AC does exactly that. It divides those two triangles right there. And you have, once again, guys, alternate interior angles right here. That's something you're really going to have to come up with and kind of seek on your own. And I know I'm doing a lot of the drawings to show you it. But that's something, again, that's through discovery. It takes some time to really hone in that practice, but there they are. We have another angle-angle case because angle BAC, this one right here, BAC, is indeed congruent to angle, let's see, B would correspond with A, and this one ACD, ACD. That is, once again, those are from alternate interior angles right there. You don't need to, well, depends on who you're with, but that's a given, alternate interior angles. All right, so what's the triangle similarity statement? This is an angle-angle thing right here. So let's call it top one ABC. So triangle ABC is not congruent, sorry, similar, is similar to triangle what? ABC goes from this known congruent angle right here in green to an unknown one to the right angle. So we got to go the known congruent one in green to the unknown angle to the right angle. That's CAD. CAD. Once again, by angle, angle. All right. I can tell this is going to be a long solution guide video, guys, or a longer set because I haven't done any proportionality yet. So those are the first 4. Taken care of. Any questions? All right. All right, this is where I said some decimal things might come into play here. I am going to still be doing, it says explain how you know whether the triangles are similar. So if I find out they are similar, guys, I'm still going to do the similarity statement. I still got to do angle, angle, side, whatever, because that's the explanation. That's how you know. But I want to write the similarity statement not only for practice, but also because I need to know which parts correspond. If I'm going to find an indicated length here, I need to write a proportion. And I can't write a proportion without knowing which parts are going to correspond. And the similarity statement is, besides redrawing something if I have to, the similarity statement is always the most assured way to do that. All right, good news on number 7. We already have angle, angle. Angle A is congruent to angle D. B is congruent with E. It's already given. So we already know that triangle ABC is similar to triangle, that's ABC. This is oriented the same way, DEF. So we know it corresponds. It's kind of alphabetical there. So by angle, angle. Awesome. Now we got to find the length of AC. All right. If possible, find the indicated length. So here's AC. Because they're already drawn the same way, AC being the first and third letter, DF must correspond with AC. That's awesome. Now here's the problem. I have corresponding parts right here where I can write a ratio, right? That's good. That's fine. 7.5 is to 15.0 as, and apparently 7.5 is small, 15 is the large. So AC is right here, is to DF. The problem is, guys, we do not know the length of DF. Listen, if I knew that the length of DF was 10, then I could totally answer this part for you. But I don't know the length of DF, and I don't think I have a way of telling you what that length is here. One might surmise that maybe this is some sort of isosceles triangle. Maybe this is 10.2. Nothing tells you that it is. Someone might say, hey, maybe this is a right angle, and use Pythagorean theorem to find out. Nothing tells you that it is. I don't know the length of DF. I can't figure it out, and it's not the harm of it's not the fault it's not the fault of this being similar to, they're similar triangles, they are. We just don't have info on DF to be able to set up the proportion that we want to cross multiply and do all this stuff to solve. Not enough info to find AC. We need a length for DF there. We need a length for DF there to do that, despite the fact that the triangles are similar. So explain how you know whether they're similar, angle, and we move on. All right, so we couldn't find AC. Too bad. All right, let's go ahead and find the next one in AD. Now, I drew some triangles like this here actually in the previous problem set, if you saw the last video here. But you do have two different triangles here. I don't know if you guys noticed. We have a triangle right here in ABC, kind of the smaller triangle, if you will. And then we have the bigger one, ADE, which is right here. ADE is that bigger triangle there. Okay. Oops, I didn't want the B to go with that. B is ADE. Anyway, they want us to find the length of AD, which is basically the length of this bigger side right here in that bigger triangle. Now, in order to do this, guys, once again, we can't just set up proportions unless we know for sure the triangles are similar. So that is really, again, your first goal. Show the triangles are similar. They didn't state it at all. We need angle, side, something like that. Now, we do see sets of side lengths here. Of course, that's to help find some, find the missing sides. But also, do we have a side angle side? Right here in this triangle ABC, I see a side here. I see an angle right here, and I see a side. It's possible maybe we have side angle side with side angle. Oh, the problem is we don't know all of AD. That's what we're trying to find. So we can't do a side angle side test with this. We can't do side because we're missing these lengths here as well. We're going to have to press our luck with angle. And if we can't get angle, then we can't show the triangles are similar. So luckily, we have parallel lines. And when cut by a transversal such as this one, that angle B in the first triangle and D in the second triangle, they are corresponding angles. And corresponding angles, when lines are parallel, corresponding angles are congruent. So those two angles are indeed congruent to each other, guys. Angle D is congruent to angle ABC. And again, I have to be specific about this one because B could have been something else here. Now, if the triangles were separate, guys, we couldn't have been able to find out that those two are congruent to each other. But indeed they are now, so I'm going to be able to mark them in the separate triangles, which is cool. All right, you could do the same thing, corresponding angles on the other side, by the way, guys. We know the transversal right there, and then parallel lines, C and E. Those two would also be congruent to one another for the same reason. So corresponding angles there does the same thing. I will show you about the top angle as well, though. Angle E in the big triangle is congruent to angle ACB in the smaller triangle right there. So these two are congruent to one another like that. We do have angle. The triangles are similar. Let me show you the top angle, though. And this is kind of a tricky thing. This is something called the reflexive property here. Angle A is congruent to angle A. Now, you might say, well, no duh. But however, it's not always true. I can make another diagram that doesn't make the angles congruent. The difference is in this diagram here, when it was made the way it was, this angle here was shared. It was a shared angle. It's the exact same thing that we're looking at in both triangles, right? Remember, ABC, look at that angle right there. ADE, look at that angle right there. Because it's a shared angle in both drawings, of course it's congruent to itself. It's the same thing. Right? It's like two bodies sharing the same head. Well, maybe two heads sharing the same body. I think that'd be a different kind of like, hey guys. Anyway, so angle A is congruent to angle A in that same kind of way. That's something called the reflexive property, where you're sharing a part in a drawing. Technically, This uses something called the reflexive property as well because it shares a side. The CB is a shared side in both of these. We're not talking about that here, but that's reflexive property in use. Anyway, definitely have angle, angle. I gave you angle, angle, angle. I'll just call it angle, angle because that's just what they say. But yeah, definitely have enough information, guys. These two triangles are similar. What do we call them? B was corresponding with D there, A with itself. So we'll say triangle ABC is similar to triangle ABC with ADE. ADE by angle, angle. Good start. Let's proceed. Let's go further. We need to find the length of AD. Let's hope we can do this one this time. Now, I think the triangle redraws really help when we split things up. I want to write the measurements where they go. This 9, this is 9. 9.0, but I'm just leave it as 9. This is 12. Those correspond with each other. They're bases, B, C, D, E. And then this is 5, and this is our unknown that we're trying to find, this AD right here. So when it comes to writing a proportion, guys, we can correspond 9 with 12. That wasn't supposed to happen. 9 with 12 right there. And then let's correspond 5 with our unknown. 9 over 12 equals 5 over the unknown AD. So 9/12 equals 5 over missing AD. You know me, before cross multiply, try and simplify a fraction if we can. 9/12 reduces to 3/4 if we divide top and bottom by 3. Cross multiplication time, guys. Let's go to work on this thing. Multiply AD by 3. So I get 3 times AD equals 4 times 5, which is 20. And if I divide both sides by 3, I get AD equals 20/3. That is the length of AD. That's also 6 and 2/3. I can't do that right. 6 and, yeah, I think 6 and 2/3. So 6.6 repeating. I'm not going to talk about it that way. 20/3 is a great, perfect answer. I'm not even being sarcastic about that. I really like that answer. Okay. Number 9. Let's find the length of QR if we find out the triangles are similar. I think they are. I have angle, angle already right here, guys. So we do have, let's call it ABC again. Triangle ABC is similar to which one here? A, the double arc's congruent side, B, the unknown, C, the single arc. P, the double arc, Q, the unknown, R, the single arc. So that's P, Q, R, which I believe is alphabetical. LMNOPQR, yeah. That's by angle, angle, by the marked drawings there. Let's find the length of QR. QR are the second and third letters here, like BC is. So BC and QR correspond with one another. AC, the first and third, correspond with PR. Those are also labeled. Looks like we can set up a proportion for this, guys. Let's go ahead and check that one out. I can do, let's do AC over PR. So boom over boom, we're going to go this way, equals 1.2 over unknown. And the unknown. All right, 2.0 over 1.6 equals 1.2 over our unknown QR. Again, hopefully you're kind of catching up with that mindset. All right, this is the kind of thing where, once again, this is 1.25 if you do the division with the calculator, but I'm going to do the decimal shift instead. Shift this over, guys. We get 20/16 equals 1.2 over QR. Heck, I might decimal shift this one. You want to do that? How do you decimal shift this one? Got to multiply everything by 10. 10 over 10. So that'll be 12 over 10 times QR. For some people, this will be a little too, like, what's he doing? That's okay. This is the part where I said, if you want to kind of skip this part and, kind of trust the process, whatever, that's fine. But the point is, what we set up is what we were looking for. All right, 20/16 reduces to 5/4 if we divide by 4. 12/10 actually reduces to 6/5. That's nice. I can do 6 over 5 times QR. All right, cross multiply time. Let's go ahead and play with that now. 4 times 6 and 5 times 5 QR. So 25 times QR equals 24. And if we divide both sides by 25, we will get QR equals 24/25, like that. You want that decimal? If you get that on a test, you get 96%. So that's 0.96 as an actual length right there. That is the length of QR. We're set. Okay. Number 10, find the length of BD. So first we got to figure out these triangles are similar. I've kind of like a blister on my thumb after all this writing. These aren't the only couple videos I recorded today. I'm doing a lot of these. Plus I taught earlier today. Okay, find the length of BD. Triangles are similar. So as two triangles, if you see the triangle, here's triangle ABC, and then here's this other triangle right here, right? BCD, or whatever you call it, DBC. They both share that 17. I think I talked about that reflexive property, right? So if I did a redraw, I'm going to draw it kind of tall. So A, B, C, here's that 17. And then this is 8.3, and then there's a right angle. I could even use, honestly, I could use Pythagorean theorem and find out that side. That might be important if we do some sort of side angle side test. This one over here, let's draw it the same way. If we're going to attempt to be able to find similarity in these things, let's go ahead and put D over here, B right there, and C up there in the same kind of way, right? This is also 17. It's a shared side, so we know that's 17. We have a pair of angles congruent. We have a pair of sides congruent, which is actually a little unconventional. We try and look for sides that are actually different sizes to set up proportionality. Now, I know that you might want to make some sort of assumption that this is also 8.3, but there's nothing that tells us that that needs to be 8.3. In fact, I think we're kind of checked out with this problem at this point. See, who knows how long BD actually is? It could have gone all the way out here. Nothing's stopping this angle from being this big, this angle from being this small, this side from being this long, and this side from being this long. Only thing we need is this to be 17 and this to be a right angle. We don't know how big those things are. I don't know that's 8.3. I can't do some sort of side angle side test, and even if I got those, I guess the triangles would be congruent, not similar. Similarity is congruent. I don't have enough info for this problem. I don't have angle. I don't have enough for side angle side. I can't do any sort of, I don't know this is a bisector or anything like that to find. I don't have enough info for this problem. This is not enough information to even figure out that the triangles are similar. I'm going to assume, well, I'm not going to assume anything about it, but if they're similar, they're also probably congruent on top of that. Actually, that's not necessarily true. The 17 might not be the corresponding part here. This might end up being 17. I'm not going to get into that. If we find a problem like that, great. But guys, not enough info for this problem. We don't have an angle or any sort of thing like that to do this, so we're done. All right, let's move forward. Let's look at number 11. All right, now we're dealing more with, looks like we have a side-side-side test worth playing with, because I see no angle measures, and you don't know this thing called the law of cosines to find angle measures, so we're not playing angle here. Show whether or not each pair of triangles are similar. If possible, justify your answer and write a similarity statement. I plan on doing all of that. I love the instruction. So I have isosceles triangles. Check that out, 16 and 16, and then 9 and 9. Now they're congruent to each other in their own way, of course, but we know which parts should correspond. Legs with legs, and in fact, since they're the same numbers, we only have to test them once. Let's check a 16 over 9 against the base lengths. 16 in the big one, 9 to the small. 5 to the big, 3 to the small. Does it equal 5/3? Well, let's try and reduce the fraction. I can't reduce that, though. 16 over 9 does not reduce. 5/3 does not reduce. I think we're stuck. Not stuck in a bad way. I think we've hit our part where we say, just like that one set with the angles and the isosceles triangles are giving us fits, guys. These two are not similar as well. I mean, I could put another 16 over 9 just to kind of bury the hatchet and say side does not apply. All these need to have the same similarity ratio. They need to grow the same amount, and they do not. These are not similar. There's a difference between not enough info and not similar. These are absolutely not similar because the proportions are known to not be identical. I'm done. Number 12. Let's start off with the vertical angles. Those are always important to establish when you have them. I don't see parallel lines for alternate interiors, so I can't play angle on this one here. So our hope is for some sort of form of side angle side right here. And what's good was the angle that is congruent is in between the sides. When you do side angle side, we can't have something like these two, which it's fine if they're congruent, but we can't say angle side. That's not the same thing as side angle side. So, okay, these are congruent because they're vertical angles. What we need to test is for proportionality among our sides. Now, here I have a triangle with side lengths 3.5 and 4. 3.5 is smaller. Here I have a triangle with side lengths 5.6 and 6.4. 5.6 is smaller. If you're going to test for these sides to grow in proportion with one another, you have to test the relatively small side in one triangle with the relatively small side in another triangle, and then relatively large with relatively large. That's the only way of ever guaranteeing any possibility of side proportionality. You don't want to test this small side on this triangle with the large side in this triangle in its own ratio. You want to go small with small, large with large. So I'm going to check 3.5 against 5.6 because those are the relatively small sides in their own triangles. And I say relatively small because 5.6 is larger than 4, but it's the smallest among the known sides here. And then I'm going to test 4 against 6.4. And once again, guys, it is a side angle side test here. So if there's any similarity, that would be cool to check out. Let's see, 3.5 over 5.6. Let's check 4.0 over 6.4. And let's see what we got. Let's try and simplify these fractions here by decimal shifts. I got 35 over 56 here and 40 over 64 here. If I divide 35 and 56 by 7, 35 over 7 is 5, 56 over 7 is 8. There I got 5/8. I can divide both these by 8. 40 over 8 is 5, 64 over 8 is 8. I got 5/8. I have proportional sides here in these. So that's a side proportional with a side, and the included angle in between does indeed give a side angle side similarity. So I can make a triangle similarity statement where I say triangle. I want to say ABC, but because we're so focused on this middle part, guys, let's call this thing BCA, going across the smaller known side to the congruent angle to the larger known side. So triangle BCA is similar to triangle, let's go D across the smaller side to the congruent angle to that one, CE. So triangle DCE there. I like that. That's by not angle angle, but side angle side similarity. Nice conjecture there. Sorry, this thing keeps glitching out when I'm handwriting. That's not my handwriting messing up there. The computer almost hiccups and doesn't register what I'm writing for a moment. All right, there's our similarity statement. I'm getting hand tired. All right, number 13 here. Once again, notice that in 13 here, we have a shared side BC in both these triangles. And, you know, if I did a redraw of these, let me do this in a nice, cleaner way here. If I did a redraw of these, I'd get, here's a triangle ABC, like this guy. I'm going to go and take it, and, oh, hang on a second. This thing's going to have fits with me. I'm going to take it and move it on over there. All right, so there's my triangle A, B, C. And then here we have another triangle BCD or something along those lines. No pun intended. B, C, D. Let's redraw that one, kind of split it apart. You know, there is that 8 that's congruent in both, right? It was a shared side. That doesn't mean the 8s correspond with each other, though. In fact, that's often not the case when you're talking about similar triangles. What I mean by that is, if I orient this, you know, by rotation, and I can't guarantee that this is the way that it looks, but I'll tell you why I think it is. Not by the looks here. But see, when I reorient this, the BC in this triangle does not correspond with the BC in this triangle. They're in different spots. BC here corresponds likely with DC. You know, we'll take a look at how these things ultimately look in the end. Let's write these things out and see what they look like this way. 20, 15, and 8. And then here, this is 8, 6, and 3.2. Now, this clearly looks like a test of side, side, side. We have to test all three in proportion with one another. And just like the last problem, guys, what we have to test is small with small, medium with medium, and large with large. We got to do everything relative to one another. And here's where I said I think that certain parts correspond. 3.2 is the smallest, 6 is the medium, 8 is the largest. 8 is the smallest, 15 is the medium, 20 is the largest. When these are drawn in this way, the smallest are both on the, I didn't want red, I said green. The smallest are both on the right side together. So let's test 3.2 with 8, small to big. As far as triangles go, small to big. Let's test 6 with 15, small to big. And let's test 8 with 8 with 20. Small to big. Come on. See, I'm writing there and it's not registering. It's doing a little, nope, don't want to do that. So let's see if these are all the same. Now, I know some people are going to say, oh, the calculator tells me one or the other. And I don't know the answer. I gotta work it out. I'm going to play with fraction reduction. I'm going to do the same thing because too much pride, guys. Too much pride for myself. That's 32 over 80 on this one. 6/15, I can divide those by 3, so I get 2/5. 8/20, I can divide those by 4, and I do get 2/5. Let's see if this one gets me 2/5 as well. I can divide those by 16. That does give me 2/5 here as well. So this is 2/5, 2/5, 2/5. They share the same similarity ratio from small triangle to large triangle. That all checks out, guys. These two triangles are similar to each other. So Because I have them drawn, that I know that the way that I state one, I can just do the other like that. So I can say triangle ABC in this one. ABC across the top is similar to BDC. Triangle BDC by side, side, side. Similarity on that one there. And as you can tell, guys, once again, the BC here, 2 and 3, are not in the same spot as the BC here, 1 and 3. Just because they're the same letters and the same number, the congruent side there that's shared by the reflexive property, does not mean that they correspond. Not necessarily mean that they correspond. You really got to see what they do next with them. And by the reorientation, this was the smallest side in this triangle, but this was the largest side in this triangle. Right? So just kind of food for thought there, for sure. All right, number 14, I have congruent angles G and R. Oh, I know where this is going. And listen, there's an opportunity to do side test proportionality. And when I see 12 with 9.6 as they're next to the 60-degree angle and larger sides together, relatively larger sides to their other parts, 10 then is next to that 12 with that 8, and I can test those. And you know what? I'm willing to bet that if I divided these, if I did 12 over 9.6, and if I did 10 over 8, I would even get the same similarity ratio. This is 120 over 96, which you divide by 24, you get 5/4. And you 10 over 8 divided by 2, you get 5/4. All this checks out, guys. I have congruent angles here. I have proportional sides here. This looks like a thing ready for side angle side, right? Side angle side. That these two triangles are similar. No. Despite everything that's here, corresponding angles congruent, sides proportional. There's nothing wrong with the math that I did. Sides proportional. I bet I can make it GHJ similar to RPQ. This is not side angle side. This is not side angle side. The angle is not in between the two sides. The angle is outside of the two sides. This is angle side side. Angle side side is not, it's ass. Angle side side is not also a similarity conjecture, and we don't have enough information to figure out, oh, maybe this one's also 60. It's equal. It's not an equilateral triangle, but you know what I mean. You can't figure out what this angle is right here. You can't figure out what this side is right here to get side, side, side. We don't have information to get side angle side out of this. And this is angle side side. Despite all the other numbers working here, the information is insufficient. We are missing other pieces of information to make our conclusion. It's on its way. It's just not ready. Having these 60s having 60s didn't help us any further. Right? They're just not there. So again, the angle needs to be in between. If we knew these two were congruent, we'd be set. But this one is not enough info. For all we know, guys, everything we have so far actually lines up pretty well. Even the angle outside of them happens to be next to the relatively longer side. Everything's lining up pretty well. There's a good chance, I don't know if it's a good or bad chance, I can't say. But there's a shot that they are similar. We just don't have the info for it. Sorry for repeating the same thing over and over. I need to enforce that. All right, 3 more problems, guys. I got an error analysis problem. Explain the error. A student analyzes the 2 triangles shown below. Explain the error the student makes. It says AB over EF is 5.5 over 4.8. So AB over EF, 5.5 over 4.8 gets 1.15. I don't know. I hope you didn't miscalculate because I'm not playing the calculator. BC over DF, BC over FD, DF, whatever it is, 6 over 6, which is 1. Because the 2 ratios are not equal, the 2 triangles are not similar. Okay, now what someone might point out is, well, says BC and this says FD. He said DF. It doesn't matter if you put DF or FD. It's still the same segment length, right? So they put FD, it's the same thing. Well, my guess is it's a number comparison thing. The fact that these 2 numbers are 6s raises a red flag for me. As far as similarity test, as we saw before, guys, those 8s that we saw didn't end up in the same spot when it came to orientation. If the 6s corresponded and were the same, then we'd probably be looking at congruent triangles. That's why this has a 1-to-1 ratio here from one triangle to the other. Those likely don't correspond with each other. These are probably not drawn the same way properly. I'm going to number these in order from smallest to largest. This is the smallest, 1, and then 2, and then 3. This is 1, 2, 3. You guys see that? These aren't drawn the same way to correspond with things. They corresponded parts that do not correspond. If we were to redraw things properly here and kind of give a better version of this thing, 4.4 would be right here. 2 would be 4.8. That would be right here. And then 6.0 would be down here. So instead, this would be D over here, E over here, and F right here. They say explain the error the student makes. Okay, so they don't ask us to solve this and do this way, but, you know, I'm willing to bet if we tested this out that the triangles would be similar. We could then do properly 5, erase this one now. We do 5.5 over, not 4.8, but 4.4. These two together. And then here we can do 6.0 over 4.8. These two right here, 6.0 over 4.8. And then 7.5 over 6.0. I will tell you right now, just by my knowledge of numbers, that indeed these are all 5/4 as a ratio. And this would then be side, side, side similarity. Triangle ABC is similar to triangle DEF by side, side, side. So a mistake was made here, not by the calculation, but by choosing which parts corresponded when they did the division. They did go from large to small, though, like as in large triangle to small triangle. That was fine. Because you can imagine someone might do even this over this and then this over that. Whatever. But yeah, there's the student's error, and it's going to happen. It's going to happen a lot. All right. 16 and 17, last two problems here. Find all possible values of x for which these two triangles are similar. So, wow, okay, so we have a lot of setups here. I'm actually, I'm thinking about this now. I'm hesitant. I'm thinking about, no, I'm fine. I was thinking about being hesitant to saying maybe I shouldn't have assigned this to my students, but they know quadratics, so I feel a little better about that now. All right, here's the thing, guys. We don't know which ones are congruent to what. We're not assuming these are congruent to each other. There's no need for that. But what I mean is we don't know whether this is congruent to this one or whether it's congruent to this one. I guess it could be congruent to this one as well, but there's no... Oh, I'm sorry. These aren't proportions. I was thinking of sides. Okay. Oh, hang on a second. Then. Let's rewind. All right. Let's look at this angle here, and let's play with different things that we think it could be congruent to. It could be congruent to this. And if it is, then you set them equal, right? If triangles are similar, I should have said this. If the triangles are similar, then what we would be saying is these two would be, if they correspond, they'd be congruent to each other. So let's check and see how that looks. 2x minus 50. If I subtract x here, then I get, if I subtract x, then I get x, I'm having trouble, equals 60, right there. Okay, so that would mean x equals 60. Now from that, because I'm playing with this idea, that would mean that this couldn't be congruent with this here, because that would say x is 70. So if that x is 70, that's no good because we already have x is 60. So the only chance of that being the case is if this was x here, which means that would be a 60 right there. You know what I mean? So if that's 60, now I haven't done this problem before, so I like exploring it with you. If that's 60, then these, I'd have to plug 60 into here. So 60 plus 10, so that'd be 70 here, which means this would be 70. Can I have a triangle that has 70, 70, and 60? No, I can't. No, that's not allowed. So solving for x under the condition that this one is congruent to this is not possible. That's not something we can do. So I'm going to axe that one right there. That's not okay. You know, I should leave that up somehow though. So a no-go on those two. Let's try this one. Let's try x plus 10 with 70 right here. So x plus 10 equals 70. Subtracting that, we get x equals 60. So, okay, if x equals 60 there, obviously that's 70. That would make this one here 60, of course, because x is 60. 2x minus 50 there would give you 70 here. 2 times that is 1 time. Yeah, so 70 here. So that becomes 70, 70, 140. That would give you 40 here, and these two would then give you 50 here. Also not congruent corresponding part. Only these two are congruent. The other possible corresponding parts are not congruent there. So that one's also no good. So it looks like I'm having some trouble here taking this x plus 10 and making it congruent to any of the other labeled parts here in order to solve for x. It doesn't seem to work out. Let's go ahead and try the x, this one here, with, say, this guy. We're going to set x equal to 2x minus 50. When I subtract x and add 50, I'm going to get x equals 50. Let's see how that one pans out. So if x is 50, then we'll go ahead, we'll get 50 degrees here. 50 plus 10 is 60 here. 50 plus 60 is 110, and then that gets you 70 here because they got to add to 80. 50, 60, 70. Let's try that. X is 50 here. 2 times 50 is, I was going to say 50. 2 times 50 is 100, minus 50 is 50, so that becomes 50. This is 70, and then that guy here would be 60 for the same reasons. So cool. Here we have corresponding parts. That one seems to work out. X equals 50 is a valid one. This was actually invalid. Invalid, invalid, invalid. So x equals 50 works. That's a possible one. There's one more that I can test to see if it works, and that's checking this angle x here against the 70. If x was 70, straight up, if x is 70, then that means obviously this is 70 here. 70 plus 10 is 80, and then with 70 plus 80, that's 150. So 30 remains here. That's 30. Let's see if this works here. 2 times 70 is 140, minus 50 is 90, and that doesn't seem to work out because this looks like this is 20 right there. Unless I did some wrong math, I think that's good. So looks like only the 70s work there. So x equals 70 doesn't seem to work either because it doesn't leave corresponding congruent angles the rest of the way. So the only possible value for x that I seem to notice, unless I'm doing something wrong there, is x equals 50. Testing all the other conditions doesn't seem to give us all sets of corresponding angles congruent. So unless I missed something else in there, guys, I think that's all for number 16. All possible values is find one value. All right, here we go. Last one, guys, number 17. Identify two similar triangles in the figure and explain why they are similar. Sorry about that. Then find the length of segment AB. All right, let's take a look at this one. Let's explore this thing here. I'm going to make it bigger. Okay. All right, here we go. All right, so here we have two congruent angles here and here. So here's the concept, guys, that I'm thinking about right now. Again, I haven't done this problem. Here's the concept I'm thinking about right now with this one. If we see this angle here, that means we're talking about this triangle. You know what I mean? I have this triangle right here, and this is one of the triangles that we need to make similar to another triangle. Now, my possibilities here, my hiccup comes in the form of where's my other triangle? And of course, it has to do with this angle here. And you might be saying, well, Mr. Robinson, clearly it's this triangle right here. Maybe. But there's another triangle that exists with this angle right here. Now, I don't know if you guys see it, but it's actually right here. Check this out. You guys see this one? You guys see that triangle right there? That's another possible one. And I'm leaning more toward this one because I don't think the other one can get me a sense of angle. Clearly, there's no form of side angle. Well, actually, there could be because this is a shared side right here. Here, let me play with this one first. I don't have any sort of, like, I don't know if that's a right angle or anything like that. You know, that's like a, you know, it's a linear pair. Right? Does that give me alternating? No. So the only possibility is if I could do some sort of side angle side, and I can't really. Even if this was some sort of x that I could find in some sort of way with proportions, it doesn't get me. Well, I can't because I don't know that they're similar yet. So I can't set anything up there. Plus, that's angle side side. So this setup here will not give me similar triangles. So the only possibility is if this other setup will, where I have this right here. And I know that this looks a little more confusing to you guys with this overlap, and especially more so when I say, do you guys notice the shared angle A? A is a shared angle in the green triangle. You see it in the green triangle? There's angle A, and you see in the blue triangle here, you see the angle A. A is a shared angle in both triangles. By the reflexive property, A is congruent to itself, right? Angle A is congruent to angle A. We do have angle now. We have, and if I redraw these, I'm going to do the best I can here. Let me just kind of Copy and paste it out. So, yeah, this problem, I like this problem. It's a nice exploration with it. So I have that one there. That's triangle ABC. And you know what else, guys? In triangle ABC, you notice that 4 and that 12 right there? In triangle ABC, that 4 plus 12 gets you 16 right there, that entire thing. So that's triangle ABC and the information that we, and the congruent angles, by the way. We have this congruent angle here and this, well, they're congruent with angles in the blue triangle. And then this one over here, when I remove, I have this triangle here, which is some form of ABD. I don't yet know what I will know what corresponds in just a moment here. But I have those guys, and that's already blue. That works out. So that is A, B, D, and this is 4. So by angle, let me delete this hunk of metal, this big thing now here. All right, so I have these two triangles here. Before I redraw them to be the same direction, and I might not, right? Maybe can you guys make a similarity statement without needing to redraw them in the same direction? I already did a redraw right here, splitting them up. Can you guys do that? I will obviously redraw, but I want you to see what parts maybe correspond without it. What do we have here? If I call this one triangle ABD, what is it similar to? Is it similar to ABC? Well, A is the 2 arc mark guy, so what has to correspond with that? Well, A. Okay, so that's A. B is the 1 arc mark guy. What corresponds with that? Oh, that was a C. That's what that was. The 1 arc mark corresponds with C, so this is C right here. And then the no arc mark, I don't know what that is, D, is with the don't know B right there. That is by angle. So they are similar by angle, and then they say find the length of A, B. They want this one or this one, however it is you want to put it here. Is that possible for us to do? Well, you know what else well, AB is the same thing, so check this out, guys. AB, I don't know what it is, but I know it's the same, right? If one's X, the other's X. I'm just going to call them AB when I set up a proportion. So what I'm going to do now, guys, I'm going to reorient this thing so it faces the same direction as the other. This one's going to be kind of tough because I can't just do this. Notice how this, I need to reflect it. I need to flip it over. So let me kind of work on that. Let's flip it over, redraw it. Obviously, when you make your similarity statement, guys, just redraw it so it's that way. You don't have to play with all this flip stuff because now I got to rewrite all these. So here I have A. Oh, what were my letters? A, D, B. So here I have A, D, B, and this is 4. All right. So here's what we're playing with. Well, I will mark these as X. If you're okay, we're going to call these X instead of A, B right there. So we have corresponding parts 4 and X. So I could say 4 over X. Here we have corresponding parts X and 16. Here we have X over 16. There is our thing, and that's where we can find AB from there, okay? Cross multiply. X times X is X squared. 16 times 4 is 64. If I take the square root of both sides here, I'm going to get X equals plus or minus 8. Lengths can only be positive. Distance can only be positive here, so we're just going to say the length of AB is just 8 there. Yes, AB is 8 in both of those guys right there. 8 and 8 with these two similar triangles. Kind of a tricky problem there. You know, sometimes when I'll be honest, you know, as you can tell, I said I didn't do these problems before. What I like to do with my students a lot is I say, yeah, that looks like a good problem. I don't know to what extent they'll go, but I like the basis of, you know, behind what the problem's providing for you to do. And I know it's going to be a challenge for students. I can't think of one of my students that's like, oh yeah, I'll know this right off the bat. Especially if this is new to them. This is something that's not new to me. I've done this a lot before. So I like that challenge. I hope that you guys did as well. And that actually was the last problem there, just showing it to you guys one more time. A very good problem, though. Sometimes I poo-poo on the questions that this book provides, but I think this is a very good, challenging one that really tests your perception and ability. All right, that was a much longer solution guide video, guys. That ought to do it for this one. This is Mr. Robinson. My thumb's got that little red spot right there. It really hurts. Thank you so much for watching, guys. Take care.